So we talked last time about indicators of biodiversity and measures of diversity measurement, but what is biodiversity? Scientists have described and formally named about, I don't know, 2 million species maybe, and some biologists think that there may be more than 10 million species that currently exist on the Earth, with others estimating as high as 100 million species. Some of the greatest concentrations are found in the tropics. Unfortunately, those are being cleared at an alarming rate. And throughout the biosphere, human activities are altering trophic structures and energy flow and chemical cycling and natural disturbances. And it's, it's a mess. But what is it? Well, it turns out biodiversity is not just the number of different species. That's just one component, species diversity. We also have ecological diversity, which is looking at the actual ecosystems. Functional diversity, looking at the roles that organisms play. Genetic diversity. Okay, all of this is a broader focus here. Okay, E.O. Wilson said that we should care about biodiversity because of an inherent connection to life. He called it biophilia. Basically, other species are entitled to life, and that's a major pervasive moral argument in biological systems. Another researcher, Brundtland, a former prime minister of Norway, he said we have to consider our planet to be on loan from our children rather than being a gift from our ancestors. And so biodiversity is a crucial natural resources that we need to protect. Even if you don't care about biodiversity for its own sake, biodiversity also plays a major role in ecosystem function, the services that they provide. These ecosystem services, you sort of see some examples here, they fall under these four major categories. Provisioning services, that's like food and water and timber. Okay, regulating services like climate and floods. Okay, cultural services like aesthetics and spiritual benefits, supporting services like nutrient cycling and water cycling and soil formation. Without these components within our ecosystem, life could not exist. And we don't have a way of replicating these things artificially. So there are benefits to protecting biodiversity for our own survival and our own economy, if nothing else. Biodiversity. And there's a mnemonic that's used in environmental that I'm going to use here, and it's called HIPCO. Okay, and there's other versions that don't have some of the letters. You might see hippo, for example, that excludes the C, but we're using this one. Okay, these are the 6 most damaging human impacts. All of them are bad, don't get me wrong, but they are basically in order of severity here. The first one is going to be habitat destruction and alteration. That is going to be the loss of habitat that's brought about through things like agriculture, urban development, forestry, mining, pollution, all of that kind of thing. And it's not necessarily just the direct manipulation and alteration. You could also have things like edge effects. Okay, edge effects like the bear, for example, that needs a large amount of undisturbed forest space, you build a road through the middle of the forest. Well, I didn't destroy the whole forest, but I've created new edging. I've altered the systems, I've altered the light, I've altered those structures, and that's going to be a negative impact. Now, it's going to be a positive impact for something like the deer or the raccoon, which is also one reason why we tend to see more accidents around those sort of roads. But we see those edge impacts having an impact either way. The I is introduced or invasive species. These are going to be non-native or exotic species that humans move either intentionally or accidentally from native locations. And because there are no native consumers and there's no sort of inherent drive to keep those organisms under control, they outplace the native species, leading to a great deal of problems. So for example, purple loosestrife and water hyacinths and some of these plants, there's been several efforts to remove them from local marshes because of the harm that they're causing. The first P that we're looking at here is going to be pollution. Human activity removes nutrients from one part of the ecosystem and adds them to another. It alters that sort of process. And so an example here is the dead zone that forms in the Gulf of Mexico because of agriculture and animal waste and human waste that end up concentrating from the Mississippi. Nutrients build up in ecosystems, and we find that they can bioaccumulate and they can biomagnify. Bioaccumulation is when the toxins enter the food web and build up within an individual organism. So over the lifespan of the organism, these pollutants will concentrate within the organism. Biomagnification looks at the impact of that on the trophic level. So as the phytoplankton is eaten by the zooplankton, and the zooplankton is eaten by the different types of fish, and then the fish eat the herring, while the amount of this pollutant, this polychlorinated biophenol, BCBs, I'm blanking right now, but as that pollution builds up, it's becoming much more concentrated and much more likely to be toxic. So even something that might be harmless amounts in the water could become incredibly harmful 2 or 3 trophic levels in. So there's toxic chemicals, especially if they're persistent chemicals, like the persistent organic pollutants, for example, that stick around in ecosystems for long periods of time. Those are incredibly complicated to deal with. Also think of something like mercury, for example. Mercury has been expelled into rivers and seas through things like coal burning and sewer. Bacteria convert that waste to methyl mercury, which then can accumulate in your tissues. And one reason why pregnant women shouldn't eat fish, because mercury levels can build up quite high. The second is population. Basically, we are overpopulated. We have too many humans on the planet. We've accelerated faster than our resources. Think back to Thomas Malthus, right? Our population is growing exponentially while our resources are not. Okay, so human population is no longer growing as fast as it was. It is slowing down within the broader focus, but we are still slightly above what's called TRF, or total replacement fertility. We're reproducing more than people are dying. The total population is still growing, and that's a factor that we have to consider. So the overall sort of population dynamics concept is basically ZPG, or zero population growth. If we can reproduce at replacement fertility, then we could balance out those systems and balance out those structures. What is replacement fertility? Well, that really depends on where you are in the world, but on average, basically about 2.1, 2.2 offspring per couple. Why? Because not all children survive to reproductive age, would balance that level. If we were slightly below replacement fertility for a few years on a global scale, we might actually deal with some of these problems. But this is sort of fairly controversial concept. The C is climate change. And global change includes things like changes in climate, atmospheric chemistry, ecological systems, all of those sort of structures. Looking at CO2, for example, people have conflict with this, but there is clearly a correlation between the CO2 levels and the global temperature. Why? Well, CO2 is one of many greenhouse gases, and greenhouse gases trap heat in the atmosphere. And greenhouse gases are absolutely essential to survival on Earth. Without it, we'd be a snowball. But we have too many greenhouse gases, and some greenhouse gases that are artificially produced are incredibly more impactful than something like CO2. Okay, so it's things to consider. Other factors are going to be things like ocean acidification, because things like CO2 turn into acid. CO2 turns into carbonic acid. So if the CO2 levels go up, it's being absorbed by the oceans and the rivers and the lakes, but that is leading to a shift in the pH of the oceans. So as the CO2 levels are absorbed, the oceans are becoming increasingly more acidic. Another factor is sea level rise. So land-based ice can melt, which is going to increase the sea level. Sea-based ice is already displaced, so there will be no impact there. So something like a floating iceberg melting is not going to change that. But say the ice shelves of Greenland, yeah, that would. Okay. Another problem is that water thermally expands. So as the planet is warming, the water we have takes up more space. So sea level is rising faster than we expected because it's not just melting. Okay, so these are some examples here. Other factors of sort of climate shift would be things like saltwater intrusion. Because we're shifting water out from coastal ecosystems, saltwater is flowing in through the water table. So there's definitely a lot more impacts than we're talking about here. And this is one of the major focuses of the AP Environmental Science class. The O is overexploitation. deforestation. This could be something like clear cutting a forest and overharvesting. This could be poaching. This could be overfishing. This could be mining in harmful ways. There are ways to use resources in a way that does not overexploit. You have to harvest with the sustainable yield in mind. But when you go beyond sustainable yield, you harm what is available. And this leads to this idea of the tragedy of the commons. The tragedy of the commons say that basically goods that are held in common are not protected. People are going to be greedy and use too much, and that we need to use things like regulation and government and policy in order to protect our common goods. There's been some disagreement, and there's definitely some conflict with the scientist because he went off the deep end, I'll be honest. But the concept is still something to be considered. Where do we do our focus? Where do we find the best means to protect and preserve and enhance for future generations? Well, there's different ideas about that too. Okay, so the first concept here is the so-called small population approach. This basically, the small population approach studies the processes that can cause very small populations to become extinct. As the population declines, the fitness declines, the genetics decline, that is going to lead to inbreeding and genetic drift, which is going to lead to increased mortality, lower reproduction rates, which leads to a smaller population again and again and again and again. That's the extinction vortex. Okay, one key factor here, though, is the loss of genetic diversity. So if we can do bringing in organisms from other areas where they've not been isolated, like we did with the greater prairie chicken, maybe that could work. But the size of a population starting down the vortex is going to vary with the organism. But what it's really looking at is minimum viable population versus effective population size. Okay, as population gets smaller, it becomes increasingly less likely that it's going to be able to be viable because of those genetic pressures. The actual effective population size, so regardless of how many organisms exist within the ecosystem, only the ones that are actually breeding are effective at preventing this loss. So if you look at the formula that's provided here, the breeding males and the breeding females are the only ones that matter. The goal here with the small population approach is to preserve and sustain above MVP. And that is going to be that viability analysis that we have to do. Modeling approaches like this enable conservation biologists to explore the potential consequences of alternative plans, but it really depends upon reliable information about the population under study, and so it's going to be much more likely to be accurate if your theoretical model is combined with field studies and observations and direct experimentation. So the greater prairie chicken, an example here, was brought back from the collapse because we were able to translocate organisms from a different isolated population and recover the genetic diversity. That's not always going to be possible because species may be endemic, they may only be found in one area. So the declining population approach is a proactive conservation strategy that's fundamentally different. So the small population approach emphasizes MVP size and interventions or things like introducing genetic variation. The declining population approach is more action-oriented. It focuses on threatened and endangered species, even when the populations are larger than MVP, and it emphasizes environmental factors that are causing the decline. Basically, you study the impacts that are causing it. You assess the population data, you study their natural history, you develop hypotheses, and you apply those results. So in this example here, they were trying to look at methods to increase the survival rate of these organisms. I am honestly not sure which organisms they are at the moment, but clearly things like nest boxes and controlling the rats are going to be a much more useful expenditure of energy and effort. And only through observation and experimentation can we actually figure out what will work. Okay. Another option is to protect areas of high diversity, things like a national park, conservation zones, eco parks, whatever you want to sort of consider it. we need to sort of look at what are our biodiversity hotspots that exist around the world. What can we do to protect those things? Nature reserves must be functional parts of the ecosystems. They need to be part of that inner structure. And we do find that sort of top-down controls where governments say locals do this don't work. You need to get grassroots involvement. You need to get low level broad population support for these things to truly be effective. The other problem is, should it be one big one, or the so-called single large, or should you have lots of small ones, this several small, so the so-called SLOS debate. And that's really something that we're still trying to study. We do find that if these small preserves, if they're not connected in some way, then there is problems sort of allowing for the spread of genes and diversity. You end up with these isolated populations. So striking that balance within this argument is something that we have to look at. What if you've actually already damaged the ecosystem and you want to bring it back? Okay, well, sort of the baseline ecology sort of has been damaged, say through mining in this example here. Okay, natural recovery is a slow and sometimes failing process. And through this, we have sort of levels of recovery. Reclamation basically just says clean up the damage that you did. Okay, make it not directly polluted, but it may not be a functional ecosystem anymore. Remediation says you're going to put in those efforts to actually bring the environment back. You're going to detoxify the polluted environment. You're going to bring plants back, that kind of thing. Remediation brings it back to a functioning ecosystem, but it may not be the type of ecosystem it was before, and we're also really bad at it, so it may not be even anywhere near as good as it was before. Restoration is the sort of the ultimate goal. You actually restore it back to a functional ecosystem of the right type. That sort of adaptive management techniques where you return it as much as possible to its pre-disturbance state. But that is incredibly expensive and time-consuming, and is not technically legally required by most governments. So it is significantly more complicated. One of the more useful techniques, though, is within that remediation focus is phytoremediation. Plants are very good at recovering pollutants and toxins and balancing ecosystems. Sunflowers, for example, are very good at absorbing radiation from water and soil. Something like willow trees can be used around landfills to sort out and clean up volatiles and dangerous chemicals that can come out of that. Indian mustard can be very good at sort of absorbing lead and arsenic from polluted soils, and then you can dig up the plants and deal with those in a concentrated form. So phytoremediation would be an example of remediation within the biological field. So bioremediation would be using living organisms at all. Phytoremediation is using plants, but it's one of the more useful and more effective tools. If you haven't sort of seen these increases in green spaces and urban environments, we've sort of had this broader focus on realizing that we are not the only organism in an area. Basically, a reconciliation ecology is an emerging branch of ecology that looks at sustaining biodiversity in human-dominated ecosystems. It's sort of a win-win environment. Invent, establish, and maintain habitats to conserve species diversity in places where we live and work. This is sort of coming out of the broader sustainable development focus, where we try to meet human developmental goals while simultaneously sustaining the ability of systems to provide natural resources and ecosystem services on which our economy and society demand. So maybe you don't have that inherent biophilia, love of life valuation, but you do care about your own survival. And we need to realize that protecting biodiversity and ecosystem services is part of that process. Sustainable businesses have said basically we want to be in business for generations, not years. So sustainable development is the only way that we can really make it work. And that's part of the overall focus of this course and, of course, AP Environmental and many of the green technologies and emerging technologies that we're seeing today.